Hi everyone, welcome to VSA Online. So today I have a pleasure hosting Dehao Yuan from University of Maryland, USA. So without any further delay, Dehao, the floor is yours, please.
Okay, thank you. Hi, good morning, good afternoon, or good evening, everyone. So my name is Dehao Yuan. I'm here to present a paper which is recently accepted by the International Conference of Machine Learning, ICML. The title is A Linear Time and Space Local Geometry Encoder via Vectorized Kernel Mixture. So as you can see later, this will be closely related to the vector function architecture or HDC, of course. So here I would first introduce what is a local geometry encoder, and I will introduce why it is important to have a linear time and space complexity. So here, let's get into the local geometry encoder. So what is local geometry encoding? So here we are dealing with the input type of point cloud. So point cloud is a collection of three-dimensional points. So as you can see here, this is a matrix M by 3. So for each point in the point cloud, we want to get the centerized neighborhood. Where if you look at this figure on the right-hand side, so this is a point cloud of a chair, and then suppose you have a point xj, which is a red star here, and you draw a ball with radius equals to r, and you collect all the points within this ball. And then what you would do is you get xk, and then you will minus xj, as you can see here. So this is the set of centerized. So then it will give you the neighborhood, the centerized neighborhood of this point xj, and you do it for all the points. So after you do this, you will get, so we want to have a local geometry encoding, which is a matrix G with shape M by D. So here D is a fixed dimensional vector. So as you may notice, for different points, it is likely that you have different number of neighborhoods. Maybe some of them have 1,000, some of them 2,000, but regardless of the number of points, the dimension D would always be the same. So that's the problem definition. So if it's written in mathematical form, it means this. So we want to get a G M by D matrix where Gj equals to encoding of the centerized neighborhood. So basically, we want to have an encoder E that receives a local point cloud and produce a vector encoding. So that's the problem definition. So here we have an implicit assumption, which is translation invariance. So it means that if you shift the point cloud by any pixel, then the local geometry encoding would be the same, because here we centerized the local point cloud. So if you shift the global point cloud by any displacement, the local geometry encoding will still be the same. So that's the problem definition. The input is a point cloud M by 3. The output is a geometry encoder M by D. D is a fixed vector. Fixed is a constant number. So why this local geometry encoding is important? Here we have I have a pipeline here which describes the purpose of local geometry encoding. So for example, if you have an input point cloud X, which is M by 3, after local geometry encoding, you get an M by D local geometry features. And then what you can do several things. First is a point-wise multi-layer perceptron. Then you can do a local regression. So for example, a typical example would be normal direction estimation. So here in this figure, as you can see, for each point, it has a normal direction. So the local geometry encoder can be used to predict the normal direction. This is by using the point-wise multi-layer perceptron. On the other hand, you can also do nonlinear regression. So a typical example would be segmentation. So as you can see, you want to segment the point cloud. For example, this may be the wing of the plane. This may be the body part of the plane. So this is called non-local regression. Why is it non-local? It is because to determine the segment of a part of a point, you need to have some more global information. So that's what I call non-local regression. So we can use a transformer to achieve that. So that's non-local regression. The third application would be condensation. So a typical example would be a classification. So basically, you want to predict or classify the entire shape or entire point cloud as a plane. So in this case, you would input the local geometry features into a pointwise multilayer perceptron and then do a maximum pooling on the first dimension. So you would get rid of the n dimension here and get a d-dimensional vector. So this d is a fixed dimensional vector. So you can predict you can do a classification on this. So in this slide, basically I want to state that local geometry encoding is a fundamental task, and it has a lot of application in point cloud applications. So after knowing the motivation, we want to know how existing work would deal with local geometry encoding. So the most important, they follow the same pipeline. So basically, they are using group and downsample. So what does this mean? So if you look at this pipeline, the input point color is n by 3. So they will first explicitly group the points together. So they will compute the mutual distance matrix n by n. So using this mutual distance matrix, you will know like what point is your neighboring point. So for example, after computing the mutual distance matrix, you will know like xk is close to xj, and therefore they are neighborhoods, and then you can group the points together. So basically, for each point, you will extract the neighboring point, and then because as you remember, the number of neighborhoods can be different for different points. So here they need to sample k points from the neighborhood, and then this will become an n by k by 3 matrix. And then they would what they would do is they use a multi-layer perceptron to lift this dimension to n by k by d and do a max pooling on the k dimension. So this will become n by d. So as you remember, this is input is n by 3 and the output is n by d. So this is how they implement how existing methods implement the local geometry encoding. So basically what they are doing is they explicitly group the points into neighborhoods and then apply a multi-layer perceptron in the local neighborhood. So this method, even though it works, but it has some bottleneck. So here the memory bottleneck is very obvious because you need an n squared mutual distance matrix here. Suppose your n is like 10,000. This already takes tens of gigabytes of memory. And also here, the n by k by d, this is also a huge dimension because if your k is large, for example, 100, and d, for example, 256, and n to be like 10,000, is already occupies like tens of gigabytes of memory. So basically, it has a huge bottleneck here, which is the n squared and n by k by d. So that's the bottleneck of existing methods. So in this paper, we want to propose a solution that solves the local geometry encoding problem, but it's very efficient to compute. So here, if you look at the computational graph on the right-hand side, this is our computational graph. So I will explain later why this computational graph will produce a local geometry encoding. But if you look at the computational graph, there is no bottleneck here. So here, P and D are constant numbers, which is 4,000. So P is about 4,000 and D is about 200. So as you can see here, there's no n squared, there's no nkd. So this is only linear about n. So it is very efficient to compute. So I will explain later why this will produce a local geometry encoding. But the motivation is it is very efficient to compute. And on the second, it's very descriptive. So this local geometry encoding, you need to tells you about the local geometry feature. And it is very descriptive. So if we do a clustering of the encoding, it will give us some very nice geometric clustering. For example, the back of the chair and the sitting part of the chair and the legs of the chair are clustered together. And thirdly, it is very robust to noise. So even though if you add noise to the point cloud, it can still produce very similar encoding. So it's robust to noise and it's very simple to implement. So basically that's the code after you convert the computational graph into code, it only involves some matrix multiplication. And here is an element-wise operation. So it only requires some matrix multiplication. So it's extremely easy to implement. So okay, so after introducing the motivation and what it is doing, so I would like to introduce how it works. So here, let's consider a point-wise local geometry encoding first. So we only consider one point, one neighborhood. So suppose you have a point cloud, which is x1 up to xn. How can we encode the distribution of this point cloud? Here is a very important observation. So suppose you have the point cloud x1 up to xn. This formula, summation k from 1 to n, exponential I, xk multiplied with a. So this will encode the density distribution of the point cloud. So basically, suppose this is the point cloud and you compute by this equation, and then you will get an encoding. And this encoding, so you can reconstruct the encoding to get the distribution of the point cloud. So that's the major observation behind. So suppose you have a point cloud, you compute the encoding using this formula. This is a closed form formula. You will get an encoding that encodes the distribution of the point cloud like this. So the major reason behind is, as we will see later on, is because this encoding is basically vectorizing the Gaussian kernel mixture. So suppose you take the point cloud and then you compute a Gaussian kernel mixture. So here is a summation of Gaussian kernel mixture. It will give you a distribution function. And this distribution function would approximate the original point cloud distribution. So here is a graph that illustrates the reason behind. It has actually has some relation with the vector function architecture. So the vector function architecture is so it states that the function with the form that the summation of like kernel can be represented by this, as long as the kernel can be approximated by the inner product of the two vectors. So here we set the vector as exponential ixa. So this will so if you do a zx and then inner product with zy, it would approximate a Gaussian kernel mixture. So that's the connection between vector function architecture. Yeah, and so if you read so here is the intuition, and if we write it into the formula, that it means that suppose the local neighborhood of x0 is xk minus x0, then the local geometry encoding can be represented by this formula. So I just basically replace this into this. So here A is a fixed random matrix where all the elements follow normal distribution. So we have a detailed proof in the paper. So we skip here. The major motivation. So the proof in the paper is basically like have a mathematical explanation about this diagram. So yeah, okay. So now we understand that for a single point, the local geometry encoding can be expressed by this formula. So suppose now we can so now we are so suppose we want to do this for sorry, do you have a question?
Yeah, a quick one. Three, is it because it's simply RGB, right? Is it because we are working with images? Why is A3 by D?
Oh, so here A3 by D is because XK is sorry, I forget to mention we assume the point is a 3D point. So here it is 3D.
Okay, so the point itself is X, Y, Z coordinates essentially.
Yeah,
Okay,
exactly.
got it. Thanks. Yeah, thanks.
Yeah, thank you. Yeah, thank you for your question. So okay, so now we have previously we have this formula for a single point. So suppose we want to compute it for all the points, then we need to, so basically this is just rewrite this formula into this. So here this I is an indicator function of whether two points are neighborhood. So suppose you want to compute the geometry encoding of J, then what you are doing is summation across all the points. And if they are neighborhood, then it is 1. If they are not neighborhood, they are 0. So that's just a rewriting of formula. So we can already compute the dense local geometry encoding if we group them and compute them one by one. So like as traditional method, using this formula, we can already do that. However, we don't need to do that because we have a very wonderful factorizability. So here, suppose we consider this exponential I xk minus xja. It can be factorized into this divided by this. So exponential I xka divided by exponential I xja. So we can factorize this into 2 components. So we can reuse a computation. So if we compute the J, which is the sparse adjacency matrix, then the dense local geometry encoding would just be equals to J multiplied with A, and then element-wise divided by A. So basically, I'm just writing this formula into a matrix form like this. Is that clear at this? Yeah, so basically, yeah, so yeah, the most important takeaway here is suppose you have so we have the point-wise local geometry encoding computed by this. So if you write it in matrix form, it would be J, which is the sparse adjacency matrix multiplied with A. A is the this formula and element-wise divided by A. So this is because we want to centerize the points. So this will give you a translation invariant local geometry encoding. So that's the version 1 of our local geometry encoding. So we first compute the adjacency matrix, and then we map the point into a d-dimensional space using this formula. And then what we will do is we multiply J with A, and then element-wise divided by A. So that's the version 1 of our local geometry encoding. So as you can see here, we still need the n squared mutual distance matrix. However, the J now becomes a sparse matrix. You don't need to, so it's only either 1 or 0. So it consumes a much smaller memory. So in this case, it's already very efficient to compute. However, we can do one more step. So we can play a trick here. So we can replace the J. Remember, J is the adjacency matrix. We replace the J with this function. So this function, if you think about this, so this is the distance between xk and xj. So for an adjacency matrix, it would be like this. So this is 1 and this is 0. And this is the neighborhood R. So this is the threshold R. So for this function, it becomes a smooth decay. Right? This becomes a smooth decay. So basically here the trick is we replace the adjacency matrix with this smooth decay. And then we use a matrix multiplication to approximate the J. So here, this J, if we replace it with a smoothified boundary, it can be approximated by B multiplied by B transpose. So here Hermitian means conjugate transpose, but you can think of it as transpose. Don't worry too much about that. So now if we replace it J with this, then it becomes B multiplied by B transpose and multiplied with A divided by A. However, in this case, you can compute this first. Compute this part first. This will give you a P by D matrix, and then you compute this. This becomes M by D. So in the whole process, it becomes linear in M. So this is what we desire. Okay, so that's the version 2. That's the version 2 of our local geometry encoding. In this case, you don't need to explicitly compute the distance matrix. So here, the distance matrix is implicitly computed by this B multiplied by B transpose. However, we can do this computation first to eliminate the computation of this very large matrix. So that's the entire motivation, entire methodology behind. And now it comes to some quantitative evaluation. So as you can imagine, this already you can think this is already saved a lot of computational power. So our method can scale to like 100,000 points. And even if there are many neighborhoods, like 640. So in this case, for the traditional method, where they explicitly grouped the neighborhoods and compute the local geometry encoding, they already experience a memory out of out of memory error when there's only like 5,000 points. But our method can scale to much larger point cloud. And we also demonstrate that our encoding is very descriptive. So here we have a normal estimation on PCPNet dataset. So basically what we are doing is we encode the local geometry encoding and then train a network to predict the normal direction. So in this case, we can show that the estimation error is the lowest among all the points. So it is much faster and it is even more accurate. So here is a qualitative evaluation. There's a qualitative visualization. So suppose you have the local point cloud like this, and from our encoding webcam can reconstruct the local shape even under corrupted input. So here is the visualization of the reconstructed distribution. So as you can see, even though the density or the noise even though the point cloud is corrupted with noise or density variation, the reconstructed distribution still looks very similar. And finally, there are some evaluation on the benchmarking data set. Those are not very interesting because later on we will see more interesting application of this. So basically, the idea is it just improve accuracy with much faster running time. This is very intuitive. And also another benchmarking data set improving accuracy and much faster running time. Another evaluation. So that's the presentation of this paper. And later on, I would present the application of this encoder to event camera. So I will pause for a second to see if there are any questions, and then if like all the questions are answered, we go back to this presentation. So I will pause for a second to ask for any question. Thank you.
Then
Yeah, I'm curious why, like, given that the way how you introduce the method, it all seemed to look more like approximation of the existing method, but then it improves the performance on these tasks. Is it because you're able to afford like more points, or like what could be sort of the intuition? Because it feels like it's more of an approximation, right? But now all of a sudden we get an improved performance.
Yeah, that's actually a very good question. So I think the major reason is this. So suppose you go back to this diagram. So as you can see here, all the other methods, they require sampling of the points. So K here, they require a sampling of the points.
Right. Yeah,
so suppose your point cloud is very dense, then your K can be very large. For example, 200, 300, that's totally possible. So for existing methods, they can only downsample the K into, for example, 32. So this will lose a lot of geometric information. But for our method, we can like consider all the points in the neighborhood. So if you look at this figure, yeah. So for traditional methods, they can only downsample. For example, this into maybe 128. That's already very large. But for our methods, they can consider all the 200 points, 300 points, 400 points. So this would give a
basically you kind of you're able to, I mean, given the fact that now you represent everything as a single, well, matrix in your case, you can allow for like flexible K effectively, right? Because then you don't have this step anywhere in between where K would be required to be fixed.
Yeah, exactly.
Okay, makes sense. Yeah, thanks.
Hi, Ross, do you have a question?
Yeah, that's very neat what you've done. Looking at the formula, you've got that division in there, and I was just wondering, I mean, because that's the result of multiplication by a random matrix in there, that some of the elements of that must be close to magnitude 0. So I'm just wondering if there's any, and this sort of harks back to um, Tony Plate's work in his thesis, where he was finding there was sort of some numerical instability in the complex representation when the magnitudes were very small. So I was wondering if there's any issues you've found arising from very small elements in that division.
I think there's no, I don't encounter this issue because here the element-wise, so first of all, if you look at this expression, this exponential I this, so if you compute the norm of A, it's always equals to 1, right? Because this is
Okay,
exponential
right.
I. Yeah, so this is not small. It has a fixed norm which is equals to 1. So there's no numeric stability here.
Okay, all right. No, thank you.
Yeah, thank you.
A follow-up sort of here. That's kind of unbinding, right? Pretty much that's what we're doing by doing the division, right? So we're using the fact essentially that kind of by doing because this is very simple to Fourier holographic reduced representations, right? And then it means here that since it's equivariant in the sense we can binding corresponds to addition, but we also can do effectively we're doing subtraction here, right? That's kind of the point, right?
Yeah.
That's very neat. Yeah.
Thank you. Yeah. That's the complex division is due to the equivariance property. So we can make like subtraction into a division. Therefore, we can reduce a lot of computation.
Yeah, that's very cool. Thanks.
Thank you. Okay. So if you have no more question, I would continue on the next part, which is another very cool application of this encoding. So it is event-based normal flow estimation, a new insight from point-based network. So first of all, let me give a very short introduction of event camera. So from this GIF, you can see event camera is when the object is moving, then it will generate events, which is on the XYT coordinate. And it has very high temporal resolution. It has wide dynamic range. It has low latency. Those are very well known. So it is very suitable for motion estimation. So suppose we want to estimate the motion of this dot, then I think it would be very, so using this event camera would be very suitable. So here is some example of video recorded by event camera. So for a traditional camera, as you can see, it captures all the color details. But for the event camera, it only has events on and off. So here blue, maybe blue and red, they are on and off. So the problem is, can we estimate like optical flow from the event camera? So optical flow means where does each pixel go at this moment. So if you look at this GIF, you can think of you are driving forward. So then of course the scene like around you would go behind. So that's the optical flow when you are driving. So you can see that the flow is like a shining. So yeah, so basically we want to can we predict some like for example optical flow from the event camera. So but here is a problem about optical flow, which is the local aperture problem. So optical flow is sometimes not decidable from the local features. So if you look at this figure, so suppose you only look at a very small local region, like here. So even though you know from very globally, the event the motion is like this. This is the optical flow. However, if you only look at this local region, you can only determine the normal flow. The normal flow is the component of optical flow perpendicular to the image gradient. So basically normal flow is one dimension of optical flow. So similarly here, so if you only look at a local aperture, if you only look at the local region, you can only estimate the normal flow. The optical flow is not decidable at this point. So here we want to, so basically now this is how we define our problem definition. We want to use the event camera to predict normal flow. So this is event-based normal flow estimation. Can we estimate normal flow from the raw event camera input like this? So the ground truth optical flow looks like that. And then here is a visualization of the predicted flow. So this is our problem definition, estimate normal flow from raw event camera inputs. So currently, there has not been any point-based network for estimating normal flow or optical flow. The major reason behind is it has a very huge event size. For example, 80,000 events per 20 milliseconds. So that's a huge event size. And it requires a refined geometry to predict. So basically, if you only downsample 32 points, 32 events to estimate the optical flow, it won't work because there's not enough geometric information. Therefore, due to this challenge, there has not been any point-based normal flow or optical flow estimator. However, our previous local geometry encoding can greatly resolve this issue, because remember, we can scale to point cloud of size 100,000 with like 600 neighborhoods. So this will be sufficient for the event camera. And we have very efficient computation. So the question becomes, can we use this local geometry encoding on the event-based normal flow estimation? And the answer is yes. So if you look at this, the methodology, it is extremely simple. So basically, let's say this is your event stream. And then for each point, you would use the local geometry encoding, which is the backend in my previous presentation. You just get the event neighborhood and then construct the event encoding and pass it to a neural network, and then you train a neural network to predict the event normal flow. So this becomes a per event normal flow. So this is an extremely simple architecture, and so I can show you some results that demonstrate the performance of this. So maybe I would expand. So on the top row, it is the ground truth optical flow. So the norm is the norm of the flow, and also the angle, which is plotted in a HSV color code. And here I also have the flow visualization. So here I have two models. The first model is trained on one data EVMO data set. The other is trained on MVSec. So there are two models. So if you watch this video, so the performance is actually very good. So the flow prediction is almost always consistent with the ground truth flow. Okay. Yeah, and maybe we can go to another video. So in this case, we estimate the ego motion from the predicted normal flow. So in this case, let's watch this video. So this is a more aggressive moving. So as you can see, this camera is moving very aggressively. And our estimator can also perform very well on this very aggressive movement. And we also have an ego motion estimator, which estimates the translation, so how your self is moving from this normal flow prediction. Yeah, so that's the qualitative result, and that's actually ends my presentation. So if you have any question, I would welcome it. Hi, Dennis.
Thank you, Dehao. So Dennis, you were first.
Yeah, I was curious how that looks. It's a visualization that looks really cool. But am I understood that correctly? That these are two different data sets.
Yeah, there are two different data sets.
Is it? And then now I'm curious, like because it's kind of maybe one hypothesis is that like maybe there is actually a universal flow estimator for natural images. Like what would happen if you, let's say, train your neural network on the one data set, but then you plug it into the other? Would the performance drop significantly? Or is it kind of data set specific? I'm curious, basically, is it data set specific, this estimator, or is it more like kind of as far as it's very similar domains, it would perform similarly?
Yeah. This is a very good question because in this paper, my major claim is our point-based network can address this domain gap very well. So for traditional method, so let me give a short introduction. So for traditional like flow estimator, what they are doing is they're using a frame-based method. So for example, you will voxelize the events into an image, and then you compare, like for example, do a matching. So like from here to here, from here to here, compute the matching. So they often use a so-called correlation volume to do this. But however, this will cause a problem. So suppose you have different data sets. So different cameras, they will have different like focal length. They will have different distortion coefficient. So especially if you, for example, look at this data set, if you look closely, the distortion is actually very large in this data set. So suppose if you look closely, the frame will look like that. And suppose if you train on the data set which is planar. So for example, the second data set I just showed, it is roughly a planar. It's a planar camera. So it does not have a lot of distortion. Suppose you train on this distorted pixels and then evaluate on another distorted pixels, then this will be very bad because the model does not have the capability to deal with distortion. So that's one major failure. And the other, it would be the focal length. So suppose your focal length is different, then your camera size would be different. Does that make sense? So in our case, all our models are trained on undistorted and normalized camera coordinates. So basically, we convert all the events into undistorted coordinates and also normalize so that the focal length equals to 1. So if we're doing that, we are able to transfer like this very well. But if traditional methods, they're indeed will have a very huge performance degradation if they use frame-based.
Yeah, cool. And maybe a follow-up here. Like, is it really critical then to have multi-layer perceptron, or can you do then, because you're already sort of in the kernel space, can you do like a kernel machine inside of that kind of kernel space, or would it perform poorly?
I haven't tried that because currently it's like the most natural implementation I can think of, and it works very well. So I'm just like stick on this. But of course, if you're already in the kernel space, maybe we can have some smarter method so that it can perform more robustly. That can be any future study. So, but currently, because I have everything, I have the ground truth flow. So the most naive implementation would use a neural network.
Right. Yeah. I was just mostly thinking that maybe since you have all the ways to compress kernel machines here in a single vector, maybe that might be even more compact than the neural network approach.
Yeah, definitely.
Yeah, cool.
Thank you. Hi, Bruce.
Sorry, another clarification question. Well, actually, two questions, if I might.
Mm,
So in the first presentation, we have three spatial dimensions. So effectively, it's like
mm,
a LiDAR point cloud.
mm, mm.
And in the second presentation, where we have the event camera, there's
Mm.
only two spatial dimensions. So are you treating it as a two-dimensional input, or are you using time as the third dimension?
Oh, it's time. So here, if you look at this
Okay.
cube, then it is
Yes.
x, y, t. This is
Yep.
t, right? X, y.
Okay. Thank you. And then the other question is, in the first presentation, it's treated in a classic machine learning batch approach. So the input point cloud matrix is n by 3.
Mm.
In the second presentation, uh, are you dividing up the input into batches? So basically, when you were talking about 80,000 events in a 20 millisecond, were you implying that you're chopping up the input stream into 20 millisecond sequential chunks and then treating each of the chunks separately?
Yeah, exactly. That's how I
Okay,
implement. Mm.
right. So it's effectively it's still a batch implementation rather than strictly online, but yeah, but short
Yeah.
batches. Okay, okay,
Yeah.
lovely. Thank you.
Thank you.
Maybe one question from my side, the
Mm.
house. I mean, you address here translation. I mean, as I mean, possible transformation of points. What about other possible transformations? How would could it be extended?
You mean rotation, like for example?
Yes.
Well, that's actually challenging because here we have a equal variance about translation. This is very nice, but we don't have a equal variance of rotation. So
Mm.
imagine suppose you multiply and rotation here, so it becomes exponential I
Yeah.
R X A. Then it cannot be like factorized into something. So at least there's no such straightforward way to factorize this rotation out. Does that make sense?
Yeah, absolutely.
Yeah, so currently I haven't had any idea like how to do the rotation.
I think Fritz mentioned, or Alpha Renner for this matter, the way how they address it by doing, well, what was it, Laplace transform or something? Ah, no, to transform to polar coordinate.
Yeah. Yeah, if you transform to polar coordinate, then the rotation becomes translation in the log polar space. But in
Mm.
this case, you will lost the translation, right?
Mm.
I think their solution was actually to live in both spaces simultaneously for that matter. So you have to preserve
Yeah.
both like Descartes coordinates and log polar coordinates, I believe.
Mm.
Okay, let's check if we have more questions in the audience. Quiet.
Mhm.
But maybe people will come up with some questions offline.
Yeah, sure.
Ask you. By the way, I mean the first paper or maybe the second one. Are they available as on archive?
Yeah. The first paper is available. The second paper is an ongoing project, so it's not available.
Okay.
So yeah, so basically if you like for example Google webcam, then it
Mm-hmm.
would be the first entry would be this paper.
Yeah. Okay. Thank you.
Thank you.
But then let's finish this session for today. So thank you all for coming, and special thanks to Dehao for this excellent presentation and excellent work. So it was really exciting to hear.
Thank
So
you.
good job. So, all right. So see you in 2 weeks from now. So I will keep you updated.
Okay, see you.
Bye. Bye for
Bye-bye.
today.
Thank you, everybody.